All right, guys, so we're going to start going over the answers to the problem review. So I'm going to work through this. It might be a long video, but here we go. So in the first one here, it reads, an 80 kilogram person stands in an elevator on a scale. What does the scale read if the elevator is doing certain things? So for part A, when we get into this one, the elevator is moving at a constant velocity. When the elevator is moving at a constant velocity, that means that the acceleration is 0 and the net force is 0. So if the net force is 0, that means that it's balanced. And when it's balanced, the normal force should equal the gravity force. So if I was drawing the free body diagram, the gravity force going down should be balanced by the scale, which is the normal force pushing up. So they're equal. And to figure out the gravity force, you just use the gravity equation, so pretty straightforward. So you just do m times g, and you do 80 times 9.8. So 80 times 9.8 gets you a value of 784. So 784 newtons is what the scale is reading when it's moving at a constant velocity, or when if it was stationary, and anytime there's no acceleration, that would be the value for the normal force. In part B, it says the elevator is now moving upward, but it has an acceleration of -2 meters per second squared. So the elevator is moving up, so it has a positive velocity, and it has a negative acceleration. So from that scenario, we've covered those before. Those two kinematics vectors are going opposite directions. When they go opposite directions, the elevator should be slowing down. So it's moving up and slowing down. So if it's slowing down, that means that the gravity force should be larger than the normal force. So if I was drawing a free body diagram, gravity, which is a constant value, that arrow doesn't change, is still mg. We know the number for that. So it's 784, and it's directed downward. That is going to be larger than the normal force going up, so that's why I have a smaller arrow in this picture. And we're looking for that idea. So some of the forces, adding up the force in the y direction, we got the negative gravity, we got a positive normal force, and that doesn't really change. Like this equation stays the same, it's just the acceleration value changes in the scenarios. That equals ma. So if we plug in, it's negative 784 plus Fn equals the mass, which is 80 times -2. So when I solve, I'm going to bring this positive 784 to the other side. So I have the normal force is equal to -160, excuse me, plus the 784. So if I subtract 160 from 784, I'm left with 624. So 624, it's supposed to be a 2, sorry about that. That looks a little better. 624 newtons, that is the scale reading, or the normal force, in part B. So this is part B. Part C, here there's a typo, but on your paper it should say it's got a positive acceleration of 2 meters per second squared. So again, same kind of scenario. This time the acceleration is positive, so the acceleration vector is going up and the elevator is moving down. So it's another slowing down scenario, but this time the normal force is larger than the gravity force because the net force points in the direction of the net acceleration. So the normal force is larger than the gravity force. Again, the gravity force hasn't changed. So that's still 784. The equation really hasn't changed, so let me try to do this real quick, where I can take a picture, and that's a little quicker than me writing everything again. If I take that picture there, that's the same equation. It's a lot bigger, but I'll shrink it. And then the value for the acceleration is the only thing that's changed. So when we go to plugging in the numbers, it's still negative 784. It's still the normal force, which is what we're solving for, the scale reading. 80 is the mass, and this time it's a positive 2. So instead of having a negative 160, we'll have a positive 160 plus the 784 is equal to the normal force. And if you do that, you get 944 for that answer. So 944 newtons is the normal force reading in part C, which is the last part here. Okay. So that was problem number 1. Problem number 2, a box is being pushed along the floor. It's being pushed at an angle 10 degrees below the horizontal, so I'll just label that the push. That angle's probably a little too steep for 10 degrees, but you get the idea. Other forces that are acting, we got gravity. The gravity force and the push have y components, so the normal force is going to be larger than the gravity force because it has to balance out both of those. And then it says there's a coefficient of kinetic friction, so it's sliding and there's friction going the other way. So FF, if you want to be really specific in your label, you can say it's called FFK for kinetic. So that's our free body diagram. We're trying to find the net acceleration of the box. This problem, because it's two-dimensional, I like using the X and Y chart that we've talked through in class before. So again, you could do this with some of the forces, but all your forces just come from your free body diagram. So we have the push, that force. We have gravity. We got normal force. And we got friction. Again, if you want to be specific, you could just leave it as friction, but if you want to put kinetic friction, you can. When we add all those up, we get the net force. If we think about this box, we realize that it's just going to go to the right. That's kind of the direction of the motion that's going to happen. So when we add up all the y forces, it's not going to accelerate in the vertical direction. So that's going to be a 0 down here. In the x, I would expect it to be positive, and my values should add up and give me a positive number. So let's go ahead and try to fill out the chart for positives, negatives, zeros. The pushing force is definitely going to the right in my diagram, so that's a positive. It's also going down, so that's a negative in the y. Gravity is 0 in the x and negative in the y. Normal force is 0 in the x and positive in the y. The friction force is negative in the x because it's opposing motion and it's not going in the y direction. So looking at this, these two downward forces are canceled out by the normal force, which is why, again, we said the normal force has to be bigger than the gravity force. And then the push, the difference between the pushing force and the friction force is going to get us our net force. So now we just have to go ahead and solve for the different forces. So let's do that. So let's go ahead and do the pushing force first. So we have the push in multiple directions. So we have the x direction and the y direction. It gives us an angle, so we're going to have to do some trick. So the push in the x, push in the y. So it would be the push, which is 30, times the x component would be the cosine of the angle. So it's 30 cosine of 10 degrees. And then for the y, it's going to be the same idea, except it's the vertical component, which would be going along with the sine function of that angle. So 30 cosine of 10 degrees is 29.5 when I rounded. If you round slightly differently, it's not the end of the world. And then for the y, it's 5.2. So I'm going to take those two values and put them in the boxes that we have. So 29.5 and 5.2. So that's the first two. We'll do gravity here. So the force of gravity is just mg. The mass was 5 and gravity is 9.8. So the magnitude of that would be 49. And that's going to go in the gravity box. For the normal force, we can solve for that now. So we're looking for the normal force here, and we're going to use the chart to help us figure that out, because there is no equation for the normal force. But when I add these two forces together, the normal force balances them out. So this is like negative 54. I put 9.2, but it's just 49. Sorry. Let me erase that there. So 49 plus 5.2 is 54.2. So it's going to be a positive 54.2 for the normal force. So that's good. We got that. We're going to need that value because we're going to solve for the force of friction. The force of kinetic friction would be the coefficient times the normal force. So when you do the coefficient, it's 0.33. And the normal force is just that 54.2 that we just solved for. And when you multiply those out, a third of 54.2 is something close to 17.9. So we're going to put that in here for the friction. Then we're going to solve for the net force in the x, which turns out to be 11.6. And then we're going to solve for A. So the net force is equal to the mass times the acceleration. So 11.6 equals 5, because that's our mass, times A, which is what we're solving for. That's the ultimate goal of this problem. We divide through both sides by 5. And the acceleration you should get is something like 2.32. For acceleration, it's meters per second squared, and it is directed to the right. So it's a positive value. So again, that means right, which is what we expected, because we expected the box to accelerate to the right. Okay. All right, so on to number 3. So in this one, a 7 kilogram box is at the top of an incline, and it tells you the value of the angle. So 25 degrees, that's the bottom of the incline here. And we want to find the coefficient of static friction between the box and the incline, so that it's at rest. So when it's at rest, it's not moving, so it's stationary. You could remember the lesson that we did in class, but I'm going to take you through it kind of the longish way, where you use the forces, because that's more of what you would need to do if you had a, like, part B. So we're going to figure out the forces in the X and the Y. There's only 3 forces acting on this this box. So when we do this, we have gravity straight down. The normal force, again, is perpendicular to the surface. The surface is tilted, so is the normal force. So it goes kind of in that direction. That's not a good picture. Let me try to get a better one. So normal force, not great, but you get the idea. It's tilted. And then the friction force is holding it in place. So naturally it wants to slide down the ramp, but it's holding it in place. So that's the friction. That diagram doesn't change for part B. The other thing we do is we tilt our axes so that the X and the Y are now parallel to the ramp and perpendicular to the ramp. And again, that's not the best picture, but you get the idea. So gravity, normal force, and friction are the 3 forces that we have in our chart here. And the net force, which is always our bottom row, our net force should be 0 because it's at rest. So there is no acceleration. So these are both zeros. So everything's canceling out. It's all balanced. So for gravity, that's the tricky one. You got to get the gravity in the X and the Y. So gravity X, gravity Y. Because gravity, we tilted our axes, gravity in the X and gravity in the Y, use trig functions because they're at an angle. And it would be mg for the force of gravity, and then for the X, it's the sine of theta. So this is one of the kind of differences in these types of problems. They change from the X being cosine and the Y being sine to reversing that. So sine becomes the X component and cosine becomes the Y. I'm going to assume that you can put that in your calculator. For when you do that, you should get 29 for the X and 62.2 for the Y. So again, those are rounded values, but that's what I'm going to put in here. So 29 and 62.2. Oh, I skipped the positive, negative, 0 stuff, so let's go back and do that. So gravity in the x is pulling it down the ramp, so that's positive in our direction, and gravity y is in the negative direction, just pulling it into the ramp. The normal force is not going in the x, friction is not going in the y. Normal is going to balance it out, so that's positive, and friction is going to balance it out, so that's negative. So once we get those two, we can fill in the rest of these boxes because they're empty. So this is going to be a negative 29, and this is a positive 62.2. So we found the two other forces, just kind of making sure that the charts balance out. And then we're going to solve for the coefficient. So the coefficient would be in the friction equation. So it's the force of friction divided by the normal force. Again, I'm kind of solving already instead of like writing out that equation, but you should recognize it. It's the coefficient times the normal force equals the friction. So it'd be 29 divided by 62.2. And this is static friction. So this value is something like 0.47. If you remember the shortcut way, if you just take the tangent of 25, you'll get that answer. That's from the lesson in class. But if you didn't have that lesson handy or you didn't remember that relationship, you'd have to do this kind of work. Really, everything is basically the same in part B, except for now there's an acceleration. So the only other thing that changes is friction. So it's not static friction anymore, it's kinetic. So nothing about the ramp has changed, nothing about the mass of the block has changed. Anyway, the mass of the block doesn't matter. We figured that out in the investigation. So really all the other values stay the same. So gravity, normal force. The friction does change because we're looking for what's the new coefficient of friction. So this is friction kinetic now in part B. The net force changes. That's really the biggest thing. So the net force has an acceleration now. So 0, this is going to be the mass, which is 7 times a positive 1.4. So if you do that, you get 9.8 for the bottom here. Gravity still the 29 and negative 62.2. Normal force is still 0 and positive 62.2. To balance it out, friction is 0, and then we have to add 29 to some negative friction value to get to 9.8. So if you do that, you'll get 19.2 for the friction. And then it's using the same equation for the coefficient. So the coefficient is the friction force divided by the normal force. So it would be 19.2 this time divided by 62.2. And when you get that, you get U is something like 0.31. So it is smaller, which is the typical idea, like the kinetic friction constant is a lower value than the static, and that has to work that way. All right. Number 4. No, that was 3. Sorry. 4. 4, an Atwood machine has a mass of 22 kilograms on one side. It's strung over the pulley. And there's a bigger mass of 30 on the other side. I'm going to call this one B and this one C just so we can label easier. And we're going to try to figure out the acceleration and tension in the cord. So it's the typical Atwood problem. It's going to go in the direction of the heavier one. That's the positive direction. So the gravity on C is going to be positive. The gravity on B is smaller, which is why it moves the way that we have it going, and that is a negative one because it's going in the negative direction. It's going against the positive. To figure out the forces on my system, which is the starting way here with this shortcut. So the system is B and C together. I'm going to figure out the outside forces on them. So it's negative gravity B plus a gravity C. That should equal the mass of B and C together times the acceleration. So I'm going to plug these things in. So it'd be negative, gravity is 22 times 9.8. And then If you do that in your calculator, you will get a value of negative 215.6, just kind of following along. And then for the gravity of C, it'd be 30 times 9.8. That one's positive, so I don't have to worry about the sign. So 30 times 9.8 is 294. So 215.6 plus 294 should get us the net force, and the mass would be 22 plus 30 for that mass of B and C together. And then we're solving for A. So this equals 52A. If I divide both sides by 52, so I'm going to do this math first where I add negative 215.6 plus 294 and then divide by 52. If you do that, you'll get an acceleration that is equal to 1.57-ish, and that would be meters per second squared. That fits on our range from 0 to 9.8, so that seems all right. And then you just have to pick one of the boxes. It doesn't matter which. I'm going to pick B. So, yeah, that's what I picked. So if I look at B, we have the tension in the cord pulling up. So box B accelerates upward, so up is positive, so tension is positive. And then we have our gravity force, which we already know for B. That's pulling down, and that's in the negative direction because it's opposing the way that this thing moves. Again, the equation is just basically adding the two forces that are in your free body diagram here. So it's the tension is positive plus a negative gravity on B. And then we always set every sum of the forces equal to MA because the net force is always equal to MA. And this is just mass B because that's the only thing in my picture this time. So the tension is what I'm looking for. Gravity C, we said was negative 215.6. For the acceleration and the mass, it'd be 22 times 1.57, our answer to part A. There we go. So I'm going to take the 215 to this side and solve after I multiplied 22 times 1.57. When I did that, I got 248.82 newtons. Again, if you wanted to check, you could take this tension and put it on block C and find the difference in those two forces and then divide by the mass of C, and that should get you back to the acceleration. It checks out. I did it on the calculator, but I didn't do it in person here because the video is already long. All right, a couple more. 5 is a, so that was all the kind of force problems in the review. Now we're getting into the work and power and energy problems. So it says a child is on a sled at the top of the hill, which is 5 meters higher than the flat horizontal surface on the bottom. So it goes like this. So I'm just drawing a quick sketch. So there's a sled and a stick figure child. There we go. It tells us the mass of the sled and the child together. And it says what's the mechanical energy of the child or system at when it's moving at 2.4 meters per second at the top of the hill. So it's moving, it's got a velocity. I'm going to call this A for part A because that's what we're trying to figure out here. So the mechanical energy at A is made up of two different types of energy. It's got kinetic at A and potential due to gravity at A. So those are the two energies. We just have to figure them out and add them together, so it's not overly complicated. So kinetic energy is 1/2, the mass is 50, and the velocity is 2.4, and we're going to square that. So I'm assuming again that you know the kinetic energy equation is 1/2 mv squared there. We're going to add that to the gravitational potential energy, which is mass, which is 50, times 9.8, times the height that it is above the 0 level. I'm going to call height 0 the flat part of the picture, so this would be 5 for that height. If you multiply those together, you should get 2,499 joules. Okay, so that's the answer to part A. That's how much mechanical energy this situation starts out with. For part B, it says there's no friction on the hill, and it asks how fast is the child moving when they're at a height of 1 meter above the flat surface. So if this is B, where I just drew the red line, there's still a height there, but it's pretty small comparatively to the height that it started at. So this child and sled are moving now, and they're going along the surface. And we're trying to find the speed when they're at B. So we're going to have to know the kinetic energy at B to figure out the speed. But the way to go about it is using conservation of energy. So in part B, we know that the energy is conserved because there's no non-conservative forces. There's no friction. We're going to ignore air resistance. So first I would say the mechanical energy at A, which we found, is equal to the mechanical energy at B. And then we just have to analyze, okay, what kind of energies are at B, sort of like what we did in A. It is the same two types of energy. So the mechanical energy at B, which is 2499 because it's conserved, should equal the kinetic energy at B and the potential energy at B, and its gravitational potential energy at B. So we can figure out this number pretty easy again from mass times gravity times height. The height is 1, so that's why we plug in that value. And I'm solving for the kinetic energy at B. So 2499 equals KB plus 50 times 9.8 times 1, which is, this is just 490. So if I subtract 490 from this, I get 20,000 or 2009 equals the kinetic energy, and then I can solve for the velocity, which is what it wants you to do. So it's 1/2 of 50, and then b squared. If you divide both sides by 25, that'll get you b squared. And then you're going to need to take a square root to get v. So the velocity at part B at position 1 meter above the bottom of the hill or the flat section is 8.96 meters per second. That makes sense because what should happen as it goes down the hill, as you sled down a hill, you go faster. So the kinetic energy is increased and the potential energy is decreased. Finally, part C wants to know, okay, when it gets to the bottom here, when the sledder gets to the bottom, they're moving at some speed, and what happens is there is friction. So there is kinetic friction here, and we want to know how far they go, what's the distance they go until they stop. So because of the friction force, they're going to stop. The friction force is essentially doing work. So that's what I said. So the work done by friction is equal to the change in energy. So you got to think about the change in energy. So it started out up here with 2,499 joules of energy. That energy transformed into different types. So the potential energy changed into more kinetic. But when it gets to the bottom here, it's still got that 2499. So the change in energy, it loses all 2,499 joules. And that's because it slows down and stops. So at the very end, the child's just sitting there on the ground. There's no height, there's no speed. So all that energy is now transformed into what you could call thermal energy, or I just call it work done by friction. So that's the amount of work done by friction. So we figured that out pretty quick. And then it's just using the work equation. So work by friction would be the force of friction times the displacement times the cosine of the angle. So we already know from doing work problems that the friction force is going 180 degrees to the displacement. So that's going to be cosine of 180, which is just a -1. So that is where the negative drops out. Force of friction is the coefficient times the normal force. It's a flat surface, so the normal force is just equal to the gravity force, because there aren't any other forces going up or down. So it'd be 50 times 9.8 or 490. So I'm going to start solving here. The coefficient they give you is 0.42. the friction force is 490, or 50 times 9.8. D is what I'm looking for, and then there's a -1 term here. So again, we have everything except the value we want, so we're going to divide by this 0.42 times 490 times -1, which is like a -205.8. That's what that number turns out to be. And so that's canceling all these other values out. When you solve for the displacement, it turns out that the sled is going to travel 12.14 meters. So that is how far it slides after it gets to the level section and finally stops. Okay, a couple more problems, just 2 left. They're more, I would say this one is the most calculus-based one. So it says a particle of mass 2 kilograms moves under the influence of force f of x, which is that. If its speed at x equals to -4 is 20 meters per second, what's its speed at x equal to 4? So we're trying to find a speed at the end. So it's changing its kinetic energy, and the relationship that I'm going to use is the work is equal to the change in kinetic energy, which is sort of what we did last problem, but this one has some calculus in it. So the other idea that we're going to use is the work is equal to the integral of the force as a function of x dx. So we're going to take the integral of this expression, so -5x squared plus 7x, and we're going to do that with respect to x, so that will work out. And we want to evaluate it from the beginning position, which is -4 meters, all the way to the final position, which is a +4 meters. Okay. The integral itself isn't too awful, so you're just using the power rule to get the values here. So it turns out to be -5 x cubed over 3 plus 7x squared over 2. And then we need to evaluate it from 4 to -4. So that's probably the part that's a little confusing when you plug in. I'm just going to assume that you can do that integration and get the solution for that period. And I got a work value is equal to -213.3. So 213.3 joules is how much work is done over that displacement. So from -4 to 4. Again, you can plug into that. You can use an online solver to help you with that too, if you wanted to. So, so then we have to solve for the speed at the end. That's what we're looking for. So if you say the work is equal to the change in kinetic energy, it's also the final kinetic energy minus the initial. We are looking, so this is -213.3. We are looking for the final speed at that. So it'd be 1/2. The mass is 2, which is convenient because that makes things nicer. And then it's F squared. So we're looking for VF. And then we're going to subtract off 1/2 times 2 times the initial velocity, which was a +20 squared. All right. So so the halves and the 2's just drop out, so that makes that nice. 20 squared is 400, so it's going to be VF squared minus 400 equals -213.3. I'm going to add 400 to both sides to solve or isolate for VF. So you get something like 186.6, and that's really repeating, but it's okay. 186.6 VF squared is equal to VF squared. You take a square root of both sides, and you get the final velocity to be 13.7, and that would be meters per second. So that is the new speed. Let's just make sure this makes sense. So the work done is negative work, so it's taking energy away from the particle. So the particle should be slowing down. So it goes from 20 to 13. So yeah, that seems to check out. All right, last one. is one that's based on a graph. So it says a particle of 0.5 kilograms moves along the x-axis with a potential energy whose dependence on x is shown below. So this is the weird function that it is based on. It says what is the forces, the force of the particle at x equal to 2, 5, 8, and 12 meters. So we need to kind of figure out how we get force from the potential energy graph or function. So the force is equal to the negative of du dx. So this is just for an x direction, and this is going to be an x direction force. So that's what we want. So really du dx, that's the slope. So it's the negative of the slope. So we just have to find the slope of each of those sections and do the negative of it to get the answer for the amount of force. So so for different positions, it has different slopes. So at x equal to 2 meters, 2 meters is here. That line has no slope, so the slope is equal to 0. So the force is equal to 0 because the slope is 0. I'll say m for slope is 0. All right, just so you're familiar with how I'm labeling this. At 5, we do have a slope. So at 5, these are counting by 2, so 5 would be somewhere around here. So the slope of that line, if we figure it out, it goes from 4 to 12, so that's plus 8, and it does it in, it looks like 2. So it's going to be the slope value is positive 4 is how I would describe it. So the negative of that would be negative 4 newtons for that force. For 8 meters, 8 meters we're here, and the slope of that line, it starts at 12, ends at negative 12, so it drops 24. So just doing the slope calculation, divided by 24, negative 24 down, and it goes, it's like 4 seconds. So that's going to be a negative 6 for the slope. And the opposite of that would be positive 6. So positive 6 newtons is the force that's acting on it at 8 seconds. And then finally, the last one is 12. And at 12 seconds, we're back at a no slope. So the force is 0. Because the slope is 0. It's a horizontal line. Okay, so that's all part A. Part B, using this graph, says if the total mechanical energy of the particle is negative 6, what are the minimum and maximum positions of the particle? So we're trying to see where the particle can get to. So if the total mechanical energy is never negative 6, these are the maximum points at the potential energy can be. So when the potential energy is the maximum, the kinetic energy is 0. So those are the two kind of positions. So if I was counting and kind of estimating coming down, it looks like that position for part B. The left boundary, I would say, is somewhere around 9 meters. And the right boundary is around 15 meters. That's what I would say the particle could move between. So if it starts here with no kinetic energy, and it can go down to negative 12 and then come back up, and it's been moving here in this section, it's moving along the slopes, but it would get the maximum position back here is at 15. So we're kind of looking for like what's the maximum left and right boundary of the well that it's in. So that's for letter B. For letter C, it says what are these positions if they 2 joules is the value. So we're going to evaluate it kind of the way. So for 2 joules is this. So we're going from here to about here. So again, kind of estimating. I said it was a little before 8, so I called it, for C, I called it 7 meters. And I said the right boundary would be somewhere around 17 meters. To kind of get the idea of where it can go to. So again, if the potential energy is at a maximum here at 2, that's like the total energy. So it doesn't have any kinetic energy there, so it can't go past that position. So those are kind of the boundaries for that one. For the last part here, it says if E is equal to 16, what are the speeds of the particles at those positions that we described in part A? So let's look at where 16 is. So 16 is way up here. So it can go everywhere when it's at 16. We just need to know that the total energy is 16, and the total energy would be the potential plus the kinetic, because at all those times it has to have some kinetic energy to get up to 16, because the maximum value here is 12. So regardless, you just have to kind of evaluate how much potential energy it has at each of those positions and then solve for K. Again, once you solve for K, K is essentially E minus U. So you get a value for that, and then so it's 16 minus whatever the U value is. And then you set that equal to 1/2 mv squared, so it's 1/2 and 0.5, and then v squared. So this is really like 0.25 v squared. So if I divide by 0.25 and then take a square root, that is essentially what we're doing to get v. So I just solve for v there. So if you take 16, v is equal to the square root of 16 minus whatever the u value is at whatever x it is. And then you can divide that by 0.25, and that'll get you v. So for evaluating these positions at x equal to 2, the potential energy is 4. So so for x equal to 2, it would be 16 minus 4 divided by 0.25 square rooted. For that one, I got 6.9 meters per second. So that's x equal to 2. For x equal to 5, the kinetic energy I had was pretty close to 8 when I got to that value. So it'd be 16 minus 8, which is 8. So it's the square root of 8 over 0.25. That's at x equal to 5. When I got that answer for v, I got 5.7 meters per second. Hopefully this is making sense. It's just basically repeating this process over and over with the different u values. When I was at x equal to 8 here, I'm at 0. So all of it is kinetic energy. So potential energy is 0 at x equal to 8. So it would be a square root of 16 divided by 0.25. So that is 8 meters per second. And then for the last one, where it's at 12, 12 is all the way down here, so it's a negative 12. So it'd be 16 minus a negative 12. So that's the square root of 28 over 0.25. That's where x is equal to 12 for the last one here. And if you do that, you should get something like 10.6. Okay, so trying to close this up because it's a long video. So best of luck on your test, guys. I'll see you later.